Colossal diesel engines deliver immense torque and efficiency, powering ships and industry through advanced combustion, precision engineering, and relentless mechanical endurance worldwide. The startup of the large diesel generator follows a clear and deliberate sequence. First, the operator performs a quick visual inspection, checking the fan belts to confirm they are tight and in good condition. Once everything looks ready, attention shifts to the control panel, and the decision is made to fire the unit up. The generator is set into island mode, isolating it from the main grid so it can run independently. After a brief countdown, the start command is given, the engine turns over, and within seconds the diesel generator comes to life, producing a deep, powerful roar as it reaches operating speed. The operator steps back while the system stabilizes and allows the engine to warm up. At this stage, the generator is running, but there is almost no electrical load, so the amperage remains very low. Next, additional load is introduced by switching circuits downstairs. As these loads connect, the generator begins to respond. The amperage fluctuates briefly as the system synchronizes, then steadily increases. The operator explains that synchronization becomes more difficult once the generator is already carrying load, but the system manages the transition successfully. Soon, the readings climb to around 450 amps, indicating that the generator is now supplying significant power. At this point, the automatic transfer system confirms that emergency power is active, and the diesel generator is fully online and supporting the electrical demand.
And then we're going to see this go up and downstairs switches.
The Nordberg radial engine represented a major step forward in large stationary power machinery when it was introduced in 1947. Unlike the inline engines that dominated the industry at the time, the Nordberg radial featured horizontally arranged cylinders with a vertically oriented output shaft. This unique layout provided several practical advantages. Originally designed to generate power for the electrolytic reduction of aluminum, the engine's configuration proved especially well suited for pumping applications, where vertical shaft alignment was ideal. One of the most significant benefits of the Nordberg radial was its compact and lightweight design. Compared to an inline engine of equal power, the radial occupied only about half the space and required a much lighter foundation. This made installation easier and more economical, particularly in industrial and municipal settings where space and structural loads were critical factors. The earliest Nordberg radial engines were spark ignition units fueled by natural gas. These engines quickly gained a reputation for reliability and efficiency. Each cylinder head was equipped with 2 spark plugs, while a single cam mounted on the crankshaft operated a gas valve for each cylinder. This valve admitted natural gas into the incoming scavenging air, ensuring consistent combustion. As demand grew, Nordberg continued refining the design for broader use in central power stations, flood control systems, and sewage treatment plants. The company later introduced diesel and dual-fuel versions. The dual-fuel engine offered exceptional flexibility, operating on pure diesel or a mixture of up to 95% natural gas. allowing operators to choose the most economical fuel combination while maintaining dependable performance. The 1945 Nordberg diesel generator represents a remarkable example of heavy industrial engineering from the mid-20th century, a period when durability and reliability were paramount. Built by the Nordberg Manufacturing Company, these diesel engines were designed to operate continuously under demanding conditions, often in critical infrastructure where failure was not an option. Nordberg engines of this era were known for their massive, rugged construction. They were produced in both two-stroke and four-stroke designs, with various configurations including inline and radial layouts. This flexibility allowed Nordberg to tailor engines for specific applications, ranging from stationary power generation to marine propulsion. In generator installations, the engines typically drove large alternators at low speeds, producing steady electrical output with minimal mechanical stress. The primary applications for Nordberg diesel generators in 1945 included industrial power plants, municipal pumping stations, and marine vessels used for both military and commercial purposes. During World War II, Nordberg played a key role in supplying engines for ships and essential facilities. In fact, in 1944, the company built the largest diesel engine ever constructed in the United States at that time, a 9-cylinder engine producing 6,000 horsepower for a Victory ship. Construction quality was a defining feature. These engines used extremely heavy crankshafts, some weighing up to 80,000 pounds, along with thick cast-iron crankcases and oversized bearings designed for long service life. Although the 1945 models primarily ran on diesel fuel, Nordberg later expanded the platform into dual-fuel versions capable of operating on both diesel and natural gas. Today, a 1945 Nordberg diesel generator stands as a testament to an era of engineering focused on strength, simplicity, and endurance machines built not just to run, but to last for generations. Before startup, the procedure emphasizes careful preparation. The fuel pump is switched on first, followed by engaging the compression relief. The engine is then rotated several revolutions to confirm that no oil has accumulated in the cylinders, preventing potential damage. Once checks are complete, the inertia starter is wound up and engaged, bringing the radial diesel to life. The Gerson radial diesel engine represents a unique chapter in American military engineering during World War II, particularly through its use in the M3 Stuart light tank. Unlike most gasoline-powered tank engines of the era, the Gerson was a radial diesel originally designed for aircraft applications, offering improved fuel safety and efficiency on the battlefield. Its compact radial layout allowed multiple cylinders to be arranged around a central crankshaft, delivering reliable power in a relatively small space. The engine is demonstrated during a test run, highlighting several practical modifications made for improved operation. Because the original main fuel pump did not draw fuel efficiently, an additional lift pump was installed above it to ensure a steady fuel supply. This modification helps maintain proper fuel pressure and reliable engine performance. The starting system was also upgraded. Instead of the original cartridge-based starter, similar to a blank shotgun shell, the engine now uses an electric inertia starter adapted from a Curtiss-Wright R3350 aircraft engine. This modernized starter proves far more consistent and easier to operate. Installed in the M3 Stuart tank, the Gerson diesel engine contributed to dependable mobility, demonstrating how aviation-derived technology was successfully adapted for armored ground vehicles. The 1950s Worthington 16-cylinder, 4-stroke diesel generator represents a remarkable era in heavy industrial power generation, when durability, simplicity, and mechanical strength were the foundations of engineering design. Built during a time when electrical demand for industry and infrastructure was rapidly expanding, this massive machine was designed to deliver reliable, continuous power under demanding conditions. At the heart of the system is a large V-configuration diesel engine with 16 cylinders operating on a 4-stroke combustion cycle. This design allowed for smooth power delivery, excellent torque characteristics, and long service life. The engine was rated at an impressive output of 3 megawatts, although in typical operation it runs at around 2.5 megawatts, ensuring reduced stress on components and increased reliability during continuous duty. Such conservative operating practices were common in mid-20th century power plants, where longevity was valued over maximum output. The generator produces electricity at 400 volts, 3-phase, making it suitable for industrial facilities, utilities, and large institutions. 3-phase power ensured efficient transmission and stable operation of heavy electrical loads. The entire unit operates at a relatively low speed of 450 revolutions per minute. This low RPM design is a defining characteristic of classic diesel generators from this period, minimizing vibration, reducing wear, and contributing to the machine's legendary robustness. The sheer scale of the Worthington generator is immediately apparent. Heavy cast iron construction, large bearing surfaces, and massive rotating components reflect an engineering philosophy focused on strength and reliability. The slow, deliberate movement of the engine during operation highlights the controlled combustion process and the enormous inertia of the rotating assembly. Unlike modern high-speed generators, this machine relies on mechanical mass and precision machining rather than electronics for stability. Worthington was well known for producing large industrial engines and compressors, and this generator exemplifies the company's expertise in heavy machinery. Units like this were often installed in power stations, refineries, mines, and emergency backup facilities where dependable electricity was critical. Many of these machines remained in service for decades, a testament to their quality and maintainability. Today, the 1950s Worthington 16-cylinder diesel generator stands as an important piece of industrial heritage. It demonstrates how thoughtful mechanical design, combined with conservative operating parameters, can result in machines that endure far beyond their original expectations, continuing to impress engineers and enthusiasts alike. The Fairbanks Morse Model 32E14 diesel engine is a classic example of heavy-duty American stationary engine design from the mid-20th century. Built for reliability and long service life, this engine was widely used in municipal power plants, water pumping stations, and industrial facilities where continuous, low-speed operation was essential. The Model 32E14 is a two-stroke, crankcase scavenging diesel engine, a design that allows efficient cylinder filling and strong torque at very low rotational speeds. It was typically manufactured in 3 or 4-cylinder configurations, depending on the required power output. Each cylinder delivers approximately 75 horsepower at just 300 RPM, making the engine well suited for driving generators, pumps, and large mechanical equipment without excessive wear. With a massive 14-inch bore and 17-inch stroke, the engine produces high torque rather than high speed. Its physical size reflects this purpose-built strength. Complete units can weigh around 60,000 pounds, while a single flywheel alone may exceed 12,000 pounds, providing exceptional rotational stability. Overall, the Fairbanks Morse 32E14 represents an era when industrial engines were engineered to run smoothly for decades, prioritizing durability, simplicity, and dependable performance in critical infrastructure applications. This old diesel power station offers a rare look into early industrial power generation in the United States. The plant was built in 1936 and once served as a major source of electricity for the local community. Inside the massive structure are 7 enormous diesel generator units, each rated at approximately 5 megawatts. Together, these machines were capable of producing an impressive amount of power for their time, reflecting the scale and ambition of early utility infrastructure. The diesel engines, manufactured by Nordberg in Wisconsin, are directly coupled to large electrical generators, forming robust and long-lasting power units. Today, the plant stands abandoned and heavily damaged. Hurricane Ida in 2021 tore sections of the roof away and shattered many of the windows, leaving the interior exposed to the elements. Although the pipelines and systems have been shut down for nearly 2 years, recovery teams still visit the site to inspect, test, and repair certain components. The weathered walls, rusted machinery, and fallen roofing clearly show that these machines have seen better days. One of the most fascinating features of the generators is their salient pole design. Each generator uses magnetic poles energized by direct current, supplied through slip rings and carbon brushes. A smaller auxiliary generator, mounted on the same shaft, provides this excitation current, allowing operators to control the output voltage by adjusting the magnetic field strength. Though silent now, this historic diesel power plant remains a powerful reminder of early electrical engineering and industrial resilience. The Caterpillar 3412 is a heavy-duty V12 diesel engine designed for demanding power applications. Known for its durability and reliability, the CAT 3412 has been widely used across industrial, marine, and power generation sectors. With a large 27-liter displacement and a V configuration of 12 cylinders, this engine is capable of delivering up to 551 bkW, or 750 brake horsepower, making it suitable for continuous and standby power systems. During startup, the engine demonstrates smooth cranking, stable combustion, and controlled acceleration, highlighting Caterpillar's robust engineering standards. Weighing approximately 141 kilograms in dry condition, the 3412 is built to operate under harsh conditions while maintaining consistent performance. Its proven design has made it a trusted power source for generator sets, commercial vessels, and heavy mining equipment worldwide. The EMD 16-567D1 diesel genset is a powerful industrial engine built in 1965 by the electromotive division of General Motors. It features a 16-cylinder, two-stroke design, with each cylinder displacing 567 cubic inches for a total displacement of more than 9,000 cubic inches. The engine is rated at 800 horsepower, delivering approximately 342 kilowatts of electrical output. Although considered normally aspirated, it uses twin roots blowers to force air into the cylinders at about 16 atmospheres. Its layout is similar to Detroit diesel two-stroke engines, but on a much larger scale. This model was reportedly used at NASA's Plum Brook Research Station to power a wind tunnel, and was among the last 567 engines produced before the introduction of the larger 645 series. The video documents the complete startup procedure of a powerful ABC diesel engine system installed on a 500 horsepower tugboat, highlighting the careful coordination required to bring a marine propulsion plant online safely and efficiently. The process begins with preparations in the engine room, where the cooling pump switch is activated. Once switched on, the cooling pump starts circulating seawater and fresh water through the engine's cooling circuits, ensuring that critical components are protected from thermal stress during startup. Next, a 250 horsepower Scania generator is started. This auxiliary diesel generator supplies electrical power to the vessel's onboard systems, allowing the tugboat to operate independently from shore facilities. With sufficient onboard power available, the mainland power supply is switched off, fully transferring the vessel to its internal electrical network. Attention then turns to ventilation. The engine room pressure fans are enabled, and fresh air is supplied through dedicated fan ducts into the engine room. This step is essential, as large diesel engines consume vast amounts of air for combustion and generate significant heat. Proper ventilation ensures a stable air supply, safe working conditions, and the prevention of hazardous gas buildup. The starting air system is then prepared. The air valve for the port engine is opened, allowing compressed air at approximately 30 bars to reach the engine's starting system. When the start button is pressed, this sequence begins automatically. First, the prelube pump is activated, circulating lubricating oil through bearings and moving parts to reduce friction and wear. Only after proper lubrication is confirmed does the system proceed to crank and start the main diesel engine using compressed air. Once the port engine is running steadily, the air valve is closed, The same procedure is then repeated for the starboard engine, following identical steps to ensure balanced and reliable operation of both propulsion units. During this phase, a low air pressure alarm may appear, caused by the significant consumption of compressed air while starting the engines. This is a normal and expected condition that resolves once the air compressors restore system pressure. With both engines running, the video provides an overview of the engine room, revealing the tugboat's distinctive propulsion arrangement. At the front of the vessel are two Voith-Schneider propellers, known for their exceptional maneuverability and precise thrust control. Power from the diesel engines is transmitted through a Voith fluid coupling, which allows smooth torque transfer and protects the drivetrain from sudden load changes. The propeller shafts then deliver power directly to the Voith-Schneider units, enabling the tugboat to perform demanding harbor operations with accuracy and reliability. This startup sequence demonstrates the complexity, discipline, and engineering excellence required to operate a high-power marine diesel propulsion system. The test run of the Pielstick PC4 marks a critical phase in verifying the performance, reliability, and operational stability of this large, medium-speed diesel engine. Developed by the French company SCMT Pielstick, now part of MAN Energy Solutions, the PC4 series is designed for high-output power generation in demanding industrial and marine applications. The test procedure begins with a controlled warm-up phase. Initially, the engine is operated at approximately 25% of its rated load. This first heating stage allows all major components such as the crankshaft, pistons, cylinder liners, and bearings to gradually reach stable operating temperatures. Lubrication systems, cooling circuits, and fuel injection equipment are closely monitored to ensure proper flow, pressure, and response under light load conditions. After about 1 hour of operation, the load is progressively increased. The engine output is raised to 60 to 70% of the maximum load, which in this case corresponds to a plant capacity of up to 20 megawatts. This step verifies the engine's ability to handle higher thermal and mechanical stresses while maintaining smooth combustion and stable speed. During this phase, exhaust temperatures, vibration levels, and fuel consumption are carefully observed. Throughout the test run, the machines are operated under real emission conditions. Exhaust gases are produced as in normal service, allowing engineers to evaluate emission behavior, combustion efficiency, and compliance with operational standards. This is particularly important for engines capable of running on both diesel oil and heavy fuel oil with viscosities up to 700 CST. Technically, the Pielstick PC4 is a 4-stroke medium-speed diesel engine with a cylinder bore of 570 millimeters and a stroke ranging from 620 to 750 millimeters, depending on the variant. Power output reaches between 1,215 and 1,400 kilowatts per cylinder, with typical configurations using 10 to 18 cylinders in a V arrangement, operating at 360 to 430 revolutions per minute. This successful test run confirms the PC4's robustness, high efficiency and suitability for continuous high-load operation in modern power generation systems. The MAN B and WME-GA is MAN's first low-speed, two-stroke dual-fuel engine. It enables efficient switching between gaseous and liquid fuels while maintaining safe and reliable operation. Featuring SGAVs on the liner wall and a robust piston ring package, the MEGA design minimizes installation costs and can be operated using existing MEGI engine knowledge. You are looking at a total of 7.5 megawatts of electric generating capacity, a system engineered, built, and operated by the United States military. These units are located at a former highly classified military installation in Syracuse, New York, highlighting the strategic importance and reliability standards behind their design. The equipment was carefully preserved and placed into long-term storage, or mothballed, in 2001, ensuring that the system remains in excellent condition despite its age. The power plant consists of 6 Worthington supercharged diesel engines, each rated at 770 horsepower. These engines are known for their rugged construction, long service life, and multi-fuel capability, allowing them to operate on various fuel types depending on availability and mission requirements. This flexibility made them ideal for military installations that demanded uninterrupted power under all conditions. Each engine is directly coupled to an electric machinery generator rated at 1.25 megawatts, forming 6 independent generator sets. Together, they deliver a combined output of 7.5 megawatts, enough electricity to supply power to more than 11,000 homes. The attached generators are horizontal synchronous machines, each rated at 563 kVA, with an operating voltage of 400 volts, ensuring stable frequency and voltage control for sensitive loads. Overall, this on-site power generation system represents one of the finest examples of heavy-duty, mission-critical electrical infrastructure. Its military-grade engineering, redundancy, and capacity make it suitable for industrial facilities, data centers, emergency power stations, or remote locations, where reliability and independence from the grid are essential. The assembly process of a massive 4-megawatt generator follows a carefully controlled, step-by-step sequence focused on precision, durability, and electrical efficiency. The process begins with the manufacture of major components and the construction of the stator core. Thin electrical steel laminations are precisely cut using CNC machines and stacked to form the stator, a design that significantly reduces eddy current losses. In parallel, the rotor is produced from solid forged steel. Depending on the generator design, it is equipped with either high-strength copper windings or powerful permanent magnets, creating the rotating magnetic field required for power generation. Next, the stator winding and insulation stage is carried out. Long insulated copper bars, some reaching up to 11 meters, are inserted into the stator slots. Each conductor is carefully wrapped with mica tape to withstand high operating voltages. Once winding is complete, the entire stator undergoes a vacuum pressure impregnation process. During this stage, resin is drawn deep into the windings under vacuum and then cured, sealing the coils, improving insulation strength, and protecting them against vibration and thermal stress. The rotor-stator integration follows. Using high-precision cranes and alignment tools, the rotor is slowly lowered into the stator while maintaining an extremely accurate air gap. This clearance is critical for electrical performance and mechanical safety. The assembled unit is then mounted inside a heavy-duty steel frame that also houses advanced cooling systems, typically forced air or water cooling, to dissipate the large amount of heat generated during operation. For diesel generator sets, the alternator is then coupled to a powerful internal combustion engine. Laser alignment systems ensure the engine crankshaft and generator shaft are perfectly centered. Both units are secured to a rigid steel base frame fitted with vibration-isolating mounts. Finally, control panels, fuel systems, and certified safety monitoring equipment are installed. The fully assembled generator is then prepared for final testing, ensuring reliable and stable 4 megawatt power output under demanding operating conditions. A large General Electric motor is being tested at the TigerTech facility. The purpose of this test run is to evaluate the motor's performance, operating condition, and overall efficiency before it is placed into service. Such testing helps identify potential faults at an early stage and prevents unnecessary failures in real operation. During the no-load test shown in the video, the motor operates without any mechanical load connected, allowing engineers to accurately measure parameters such as no-load speed and no-load current. The testing procedure includes thorough pre-test inspections and continuous monitoring throughout the run. Special attention is given to vibration levels, abnormal noise, overheating, and irregular electrical readings to ensure the motor meets safety and reliability standards. The machining of railway wheels is a critical part of keeping trains safe and reliable. Using advanced Mobin turn lathes, train wheels are reprofiled with an accuracy of up to 1/100th of a millimeter, ensuring perfect geometry and smooth rolling. Each train is controlled entirely by electronic systems, allowing precise positioning during machining. Freight wagons handled in the workshop can carry loads of up to 100 tons, requiring robust and highly accurate wheel maintenance. Every year, around 5,000 components are revised and refurbished for reuse, supporting sustainability and cost efficiency. Passenger trains, equipped with more than 20 processors, undergo strict inspections. Ultrasonic testing is used to detect material cracks up to 2 meters deep inside the wheels and axles. In total, about 400 locomotives and wagons pass through the workshop annually, highlighting the scale and precision of this operation. The IH Solar gas turbine generator, commonly identified as Model GS350, is a genuine industrial power unit originally developed by International Harvester and later produced under Solar turbines. Although it is an older design, this machine was built for reliability and continuous operation in demanding environments. The GS350 is typically coupled with an IHT350 or KS350 gas turbine engine, forming a complete, self-contained generator set. With a rated output of approximately 350 horsepower, the generator can deliver around 225 to 250 kilowatts of electrical power. This level of output is sufficient to supply emergency electricity for critical facilities such as hospitals, data centers, or offshore oil platforms, and even enough to power a small neighborhood under the right conditions. One of the key advantages of this turbine generator is its fuel flexibility. It can operate on natural gas or liquid propane, and some versions are also capable of running on white kerosene. Designed as a true industrial workhorse, the IH Solar GS350 is known for its durability, smooth operation, and long service life when properly maintained. Even today, it remains a strong example of early industrial gas turbine engineering applied to reliable on-site power generation.